So this is our last week in forces and fields. And this week we're going to be talking about generators and Lenz Law. So generators are really just an application of our third hand rule. In the introduction videos to this week, Veritasium shows kind of a very simple generator that was made by this guy, Michael Faraday. So Joseph Henry, Michael Faraday, each showed that you could actually use a changing magnetic field to produce current, because we kind of know with our hand rule the other way that if we have current, so a moving charge, we're going to have an external magnetic or a magnetic field that's produced anytime there's a moving charge. And so they kind of flipped it where we could also go the other way. So if we have a changing magnetic field, we could have a moving charge. Now, in the experiment that he did, so there's a battery here, an iron ring, and then an ammeter, which measures current on that side. They found that current was only measured when that switch was turned on or off. If it was just kept constant, then the current was still zero. So the idea there is that switch needs to go on and off, and it needs to be changing. If we look at this, like maybe just when we turn it on, so the battery's here, so that's the positive side of a battery, there's the negative side. So the electrons are going this way, and they're wrapping under. So I'm using my second hand, so my fingers wrap under, which means that that is the north end of the magnet, and the south end. So if we follow those magnetic field lines through there, this is the north end, and this is the south end. So it produces, or we induce, I guess we'd call it, current in this wire. And in order for there to be current there, then I guess the electrons are going, my thumb goes down, it's my left hand, and my fingers curl over this way. So electron flow is this direction. So Faraday figured out that a changing magnetic field could produce current on the other side, and we call that induced current. So this is the big idea. So the magnetic field needs to be changing, and if we do that, we can produce current, and that's what a generator does. We have some type of coil, we have some type of magnetic field, and we either move that coil or we move that magnet, and then we can produce current. Now, we can determine these and kind of use some of our hand rules. Now, the big idea, and this is new, is that when we talk about generator effect and Lenz law, Fm, so the magnetic force opposes the applied force. We don't get energy for nothing. So we need to actually do work in order to get energy. So the magnetic force, this is talking about our hand rules, opposes the applied force. So in this example here, the wire is pushed down, right? That's the applied force. The applied force is down. Now the guiding principle is that Fm opposes the applied force. So if the wire is pushed down, Fm is up. Now, if we think about our hands, well, that's our palm. So my palm is facing up. My fingers are going into the page. So these are my fingers. So I'm using my third hand. So my palm is up, my fingers are into the page. And what we're left with is my thumb is pointing to the left. So the electrons will be moving through that wire to the left. So the big idea is that Fm opposes Fa. So here I have three coils that can generate Lenz's law. So I have a magnet here. So if I look at this magnet, okay, so you see that it's going out from here. So this is the north end of the magnet. If I take this magnet and put it in this coil, you see that the needle deflects. Now something happens where when it goes in, the needle deflects one way. When it comes out, the needle deflects the other way. And that happens in all these coils. What does change is as the coils get bigger, the amount of deflection gets bigger. And that should make sense because more coils means there's more charge, so there should be more current. Now, so when I go in, you see that it deflects to the right, and when I go out, it deflects to the left. We have so this coil I have, this wire goes underneath and then wraps around here, and then this one connects that way to there. So let's see kind of which way it's going. So if I go here, so if it deflects that way, so my finger's going around, this is going over. So if it's deflecting to the right, the current is going through here to the right. That means my fingers are curling over this wire here, and this is the north end of the magnet. And this is the north end of this magnet. So when it deflects to the right, I'm going in. Now that should make sense because in Lenz's law, Fm opposes the applied force. And in order to oppose, so this north end, if it's going in, this needs to be the north end of the magnet. And my hand rule supports that. When I go in, it deflects to the right. When I go out, now it deflects the other way. So I follow this around, so now it's coming over this way. That means that's the north end and this is the south end. So when I go out, it is opposing it because this switches and becomes the south end. So the poles of this imaginary magnet inside continually switch because Fm opposes the applied force. If I were to go all the way through, so initially, so this is the north end, it deflects to the right. As I go through and pull it out, now it deflects to the left because again, this becomes now, this is the south end and this becomes the north end. So this is the north end when it goes in, and then this is the north end when it goes out. So the magnetic field is constantly switching because this magnetic field is constantly changing. And because that magnetic field is switching, the direction the current is going is changing as well. Now, Lenz was the first guy who did this. He used a bit of logic to determine kind of what was actually happening. Because there's really two ways that it works. This is the wrong way. So this is not what happens. But if we think about this situation, if this magnet goes in here, so there's Fa. If Fm does not oppose that, so you'll notice we have a north and a south pole. So that is an attractive force. So if Fm is the same direction, we would expect that this magnet would be sucked through, right? So that magnet would be pulled through, and that's not what we actually see, right? If we were to let go of that magnet, it would just fall. So this way is not what actually happens. This is the wrong way. If we look at this way, though, so if I were to push this magnet in, so here's my applied force. In order for Fm to oppose my applied force, so be the opposite direction, so Fm is this direction, I need to have the north pole of the magnet there, right? This needs to be a repulsive force. It needs to oppose it. So as I push that north pole of the magnet in, this needs to be north. That will oppose it, and then in that way, I'm doing work. I am working against a resistive force, which means I'm generating energy because I'm doing work and I'm changing the energy. So we need to do work. So this is the right way. So if we push it in, that's what it looks like. Now, it does change. So if I were to all of a sudden now, so maybe I don't push it in, now I pull it out. So now the magnet's going that way. So now my applied force is to the left. Fm needs to oppose that. So Fm is to the right. In order to oppose that, this is still the north end of the magnet. This needs to be the south end, which makes that the north end. So if I move away now those poles are flipped. And because those poles are flipped, now the direction of the electron flow will be flipped as well. This is AC current or alternating current. Because that magnet's changing direction, so is the direction of the current. So it's not always moving in one direction. So in summary, Lenz Law says that the induced electron flow creates a magnetic field that makes moving the external magnetic field difficult to do. The big idea there is that Fm opposes Fa. Fa is the way we're actually moving something. So if we're moving the magnet, that's our applied force. What direction are we moving it? Fm is our palm, or it's an attraction between them. And that's kind of how we go about analyzing these situations. So Fm opposes Fa. We use our hand rules. Thumb is still the direction that the charge is moving. Fingers are the direction of the external magnetic field. For solenoid type questions, we determine the direction of Fa. So what is my applied force? We determine, okay, Fm needs to oppose that. And then we figure out the poles of that imaginary magnet in the coil based off of which direction Fm needs to be. If I have a north pole moving away, then there needs to be a south pole in the coil to attract it. If I have a north pole moving towards, then it needs to be a north pole in order to resist it and repel it.